problems related to Chebyshev's inequality.
So this is problem number 10 in the list, which involves Chebyshev's inequality. Tell you the average and standard deviation of lifetimes of light bulbs manufactured by certain factories are respectively 800 hours and 50 hours. So we have 800 hours as the mean value, 50 hours is the standard deviation. What can be said about the probability that a random light bulb lasts at most 700 hours. Can I erase this? Yes. First of all, let X be the bulb life for a randomly picked bulb. And I know that the expected value of X is, given that that is 800 hours, in hours. And the variance of X is 50 squared. The standard deviation is 50, right? Okay. So you asked about the probability that that's at most 700 hours. What is that X is at most? 700. And then just look at probability. Let's look at X minus the mean. Mean is less than or equal to minus 800. we have bounds for this, right? Okay, so this has the distance from this to 800 is less than or equal to negative 100. So that means, x minus 800 less than or equal to negative 100. That means the distance from the mean is more than 100. Okay? So x. So we have 800. So the probability that x is less than or equal to 700, that means x is somewhere here, that means the distance of x from 800 is more than 100. And this is bounded by the probability that, this is put in a slightly more complicated way. Does this make sense? So x minus 800 greater than 100 is either x minus 800 is greater than 100 or x minus 800 is less than negative 100, right? Okay. So this is going to be, so it's probability that x minus 800 is greater than 100. So therefore, this probability is smaller than that. The probability that, so basically I'm just looking at this on only one side. So probability that x minus 800 is greater than 100 is probability of lying here or here. I'm only considering this probability. So this probability is less than this plus that, right? Okay. So this probability, yeah, probability that x minus 800 is greater than 100. This consists of this region plus this region. And this probability consists of the probability of this plus the probability of being out here. Okay?
How is that less than negative 1? How is it less than?
You mean, oh, okay, and on this place I can put equal, that's also okay. Yeah. As I said, don't worry too much about the equal sign, it's not going to affect the bounds much, at all actually. Alright, so this probability is this plus this probability. I'm only interested in this probability. So this probability is going to be less than this probability. Because this probability contains both the probability that x is less than or equal to 700 plus the probability x greater than or equal to 900, right? So this probability is bounded above by this probability. This I can bound by a Chebyshev inequality. So maybe I didn't have to go through all this, but you can see that probability x less than or equal to 700 is bounded above that by this probability. So if this is not clear what this probability is, this probability x less than or equal to 700 plus the probability that x is greater than or equal to 900. And this now I can bound by my Chebyshev's inequality, which says that it's bounded by the variance of x over 100 squared. And the variance of x is 2500 over 100 squared. 100. So that probability is bounded by 0.25. So remember, our Chebyshev's inequality is only once you've got it in this form. This only consider this part. Okay? Chebyshev's inequality is for this and this. That is, the distance is more than 100. If the distance from 800 is more than 100. So it's either out here or here. So I first bounded this by this probability, and then bounded that by Chebyshev's. But the idea is you eventually want to bound it by something like this so that you can use Chebyshev. So if you have a one-sided probability,
So you said that the X minus 100 greater than 100.
X minus 800.
Right.
Yeah. You know,
Is-
maybe I should just erase this part so that I feel maybe this is confusing people. Yeah. Let's just say this. X less than or equal to 700 is bounded by that.
Why wouldn't it be the negative 100?
Say that again.
Oh, never mind. I think I got it. Give me a second.
So is that the answer to your question, though?
Yeah.
0.25 is?
Yeah, so what we have is that what we can say about this probability that it does not exceed 25%.
Oh, okay, so it's gotta be left, gotcha.
Right, okay.
Gotcha.
So I'd say that I could get a bound on this probability of 0.25, so that means the probability of this happening is less than 25%.
That makes sense.
Okay? All right, okay, so let me write this down again. So this is less than or equal to probability that the distance of x from 800 is more than 100. And this I then bounded by. I'm looking at the distance of x from 800, and if this distance is more than 100, then either it should be less than 700 or more than 900. That's what this is referring to. This region and this region. This is only referring to this. Probability x less than or equal to 700 is bounded by the probability that the distance from 800 is more than 100, and then I use Chebyshev. So what can we say that the probability that a random light bulb lasts at most 700 hours? The probability that a light bulb lasts at most 700 hours does not exceed 25% or is less than equal to 25%.
So it wouldn't be
So
safe.
less than 25% of the time, you have a light bulb that lasts at most 700 hours.
It wouldn't be safe to assume symmetry and say 12.5%.
We don't know that this probability is equal to this.
Right.
So we don't know anything about our distribution. Okay? So all we know is that definitely this probability is going to be less than this plus that. So we can only bound about. Any more information, we would need to know something about the distribution.
With a problem like this, if we weren't told that was Chebyshevs that we should use, we have the information to also do Markovs. Will Chebyshevs always be more precise, or should we test both to see?
Well, here, yes, we can start by just doing Markovs. So let's do Markovs. What we get here, do we have mean? Yeah, 800. So 800 over 700. See, that's not helping us too much because that's giving us a value more than 1. So, so you use the extra information. So clearly you can see Markovs would help if your mean was very small, okay? Because then you really would get a small bound. Right? But otherwise, I think in this case, yeah, this certainly helps.
Now, what if we're only given expected value and it was over 1? That wouldn't tell us. That wouldn't tell us anything, correct?
Yeah. You
Okay.
can say that this doesn't give
Not
any
that
information.
yeah.
Say 1 and then.
Right.
So usually with Chebyshevs it helps, and why does Chebyshev help? Because when you do the bound, you put the square of this in the denominator. So you're potentially dividing by some very large number. Okay? So you expect that with Chebyshev you should get a better bound, okay? Unless it turns out that this is a pretty small number. All right. So yeah, but the right thing to do would be first check Markov's, because it's so easy to check. Okay? If you get something that's more than one or more, doesn't help you at all. So you move on to Chebyshev's, okay? And with Chebyshev's you've got a bound of 25 1/4, which is actually pretty good. All right. And then problem Chebyshev's. No, okay. Let's do another problem with Chebyshev. Average post office handles 1,000 letters, and you know that you've got to use Chebyshev when the only information you have is average and standard deviation. So that's the one hint when to use Chebyshev. Or I actually explicitly say on the problem use Chebyshev. On an average, the post office handles 10,000 letters a day. Variance of 200 of 2,000. What can be said about the probability that this post office will handle between 8,000 and 12,000 letters tomorrow. So again, that x, we define our x. Our x is just number of letters tomorrow. Number of letters that pass through the post office tomorrow. And you are asked to say something about the probability the post office will handle between 8,000 and 12,000. Probability that x is between 8,000 and 12,000. Now you've been asked to say something about a probability when all you know is the mean and variance of this. So that's this hint that you've got to use Chebyshev's. Also, you see that the variance is 10,000, and very conveniently I've asked you for a probability which is symmetric about 10,000. So here, let's subtract 10,000 throughout. And basically this is that the distance of x from 10,000 is what? So it's less than 2,000, right? the probability that the distance of x from 10,000 is less than 2,000. Now, our Chebyshev's is when the inequality is in the other direction. So let's see, I'll take that x minus 10,000 greater than or equal to 2,000. All right. So we can bound this above by something, so then 1 minus that gets bounded below by something, right? So it's 1 minus, you have the variance of x over 2,000 squared. This gives you 1 minus, the variance is 2,000, this variance 2,000 squared. This is 1 minus 1 over 2,000, so you get 1, 9, 2,000. This might be 18. Right. So you've got that this probability here is greater than or equal to 0.9995.
Wow.
So you've got, so you know that almost surely, I mean, so with something very close to probability 1, the number of letters will be somewhere between 8 and 12,000. So remember, the Chebyshev's inequality bounds this above by something. So 1 minus that gives you a lower bound, right? So it's important to get your bounds right. And also, you see in this problem, if you mess that up and you ended up with this is bounded above by 0.9995, well, apart from the fact that it would be wrong, it's also it wouldn't give you that much information because this is saying your probability is something that's less than or equal to something close to 1. But anyway, you know this probability does not exceed 1, so that wouldn't give you much information. But knowing the lower bound is this means that this is a very likely event.
So when you summarize at the end, do you say that the probability is between 8,000 and 12,000, or that the probability of the absolute value is less than 2,000? And both are accurate.
Right, you can say both. But since the question was phrased as between 8 and 12,
You should
stick with the way it's been phrased. So the question asks you the probability that's between 8 and 12. Say that with probability almost 99.95% of the time, this the number of letters will be between 8,000 and 12,000. Or tomorrow there's a 99.95% probability that the number of letters will be between 8 and 12,000. All right. So we've done 2 of the problems on this list. These are the last 2 problems dealing with Chebyshev's. You have 2 problems of central limit theorem on this, then 2 problems with moment generating functions, and the rest is basically about joint distributions. Joint distributions where you calculate the expected value, the covariance, the correlation, or conditional probabilities involving, so you have the joint distribution as you have the conditional probability. So these are the kinds of problems you can expect on the exam. All right, so as I said, I'll post this online. I didn't want to print this out because I thought I might add some more problems, but I think 11 problems should be enough. All right, on the exam you have, okay, I don't want to say anything yet about the exam. So far, I've
There's an exam?
Huh? There's no exam. So the exam is next Wednesday? Yeah, next Wednesday, April 24th. You heard me wrong.
Still trying.
No, it's very much in class, and so far it's 6 problems. I might add more.
No.
Anyway, 6 problems. You have 1.5 hours for the exam.
Oh,
Okay.
you said full class time last time. You said full 2 hours.
I mean, yeah. I mean, you can take more than that. Okay.
Thank you. Love you.
But I think it's an exam that shouldn't take more than 90 minutes. But yeah, you have the whole class time.
If you do add more, will it be like we pick? Or
Yeah. Okay. Yeah, I have no choice, but choice
You do like
is
6 out of 9 questions. 6 out of 9. If it's still 6, add the extra 3.
just add the extra 3, yeah.
Say like 6
But
out of 9.
the
When
thing
you do like this would be great.
Well, I'll see about adding more problems, but the thing is, I don't want it to be such that you guys leave out like a whole section. I want your exam to have,
Every section, you still do one or the other for this question.
Well, you could do, you know, chapter 6, problem 1, 2, 3, pick 2 of 3. Chapter 7,
Yeah.
1, 2, 3.
Anyway, are we done?
oh yeah, are you guys, I completely wonder, are people coming on Wednesday or not?
Yeah.
I am.
Yeah, absolutely.
Yeah. Okay, because we have evaluation to fill out, so if you don't turn up on Wednesday, remember I'm grading your exam. Yeah. So it's last chance. To stay in my good graces, do you want to do the evaluations today or Wednesday?
Wednesday.
Okay, all right. You don't turn up, you know what's happening in your exam.
Might as well just do them tonight. I don't think anything else is gonna go right.
But yeah, we have that.
Alright.
We filled out. You want to take home?